Hi everyone, it's Mr. Hamilton here, and this video is all about radians, special angles, and the unit circle. The diagram you see in front of you, we're going to develop by walking through what radians are, why we use radians, then we're going to look at the special triangles, how we get the angles from them, and finally put that all together on the unit circle. So the first question we want to deal with is why radians? Why are we actually using radians and not degrees when we start looking at the unit circle? Well, let's draw a couple things from this. Let's draw first off, this is some angle, theta, and this has a radius from the center of the circle, r. And this along here, from that point down to that point, is the arc length. And so if you take the arc length and you divide that by the radius, then that is a ratio that we could calculate. And in fact, the arc length divided by the radius, if those two are the same and that ratio is 1, then what that means is that is 1 radian. 1 radian is when the arc length is equal to the radius. And so the idea here is if you wanted to go as far as a whole circle, for an entire circle, what we end up getting is we end up getting an arc length, and we divide that by the radius. If we actually look at what the arc length is, that's the circumference of a circle. And so if that's the circumference of a circle, well, divided by the radius, we'll just call that r, is 2 pi r divided by r. And so for an entire circle, we get 2 pi as our angle measurement if in fact that angle measurement is the ratio of the angle length, arc length, to the radius. And so this is what we're actually measuring here. We're saying the angle is the arc length divided by the radius, and so that's how we get 2 pi for an entire circle. And so what that means is that 2 pi radians is going to be equal to 360 degrees, or pi radians is going to be equal to 180 degrees. So that's why it's super helpful to use things in radians, and that's why we're going to do that now as we look at the special triangles and we look at the unit circle. So in order for us to look at the special triangles, we're going to consider two objects. We're going to consider a square with all the side lengths 1, and we're going to consider a triangle, an equilateral triangle, with all the side lengths 2. I'm going to focus in on the square first. What I'm going to do is I'm just going to draw a diagonal on the square, and we are going to focus in on the triangle that's formed on the bottom right here. Now because this is 90 degrees, the other two angles have to add to 90 degrees, and so each of these has to be 45 degrees because this is forming an isosceles triangle. Now, we said 45 degrees is now going to be radians, so we're going to get rid of the 45 degrees, and 45 degrees is pi over 4 radians. So pi over 4 radians. That's now the angle in radians. And so what we can do here is we can go ahead and we can figure out what sine, cos, and tan are. So let's just first list that sine is the opposite over the hypotenuse. And so if we're figuring out sine of that angle, we would say that sine of pi over 4 is going to be equal to 1, that's the opposite side if we're focused on this pi over 4 down here, over the hypotenuse. Well, what is the hypotenuse? Well, let's call that c. We have to solve that to determine what that value is. Because this is a 90-degree triangle, we can say that c squared is equal to the other two sides added together and squared, which means that c squared is equal to 2, 1 squared plus 1 squared, 1 plus 1, which means that c is the square root of 2. That's the exact answer for c. And so that being the square root of 2 means that's my denominator when I go the opposite over hypotenuse. So sine of pi over 4 is 1 over root 2. And so what I need to do here is I need to rationalize the denominator. And so we just multiply by something that's the same on the top and the same on the bottom. And what that does for us is it cancels out the square root on the bottom, because root 2 times root 2, any square root times itself, is the number that's under the square root. So this gives us the square root of 2 over 2. So sine of pi over 4 is the square root of 2 over 2. If we move to cosine, cosine of an angle is the adjacent over the hypotenuse. And you can see here that the adjacent side is 1 over the square root of 2. And so that's the same as it was for sine. So if we're doing cosine of pi over 4, we end up getting 1 over root 2 again, which ends up ultimately being root 2 over 2 as well, for the same reasons, because we have to rationalize the denominator. So if we did tan of theta, tan is the opposite over the adjacent. And so what's the opposite side? Well, the opposite side is 1, the adjacent side is 1, and so we end up getting just that tan of pi over 4 is going to be equal to 1 over 1, which is just 1. So now we'll look at the equilateral triangle down below. What I'm going to start by doing is drawing a line straight down the middle, and what that's going to do is it's going to form a triangle on the left and on the right. We're going to focus on the one on the left. And because that line straight down the middle cuts that bottom side in half, this length down here is 1. And then the height is something we need to determine. And so because the height is not the hypotenuse, 2 is the hypotenuse, we would say that 1 squared plus the height squared is equal to 2 squared. And then we can rearrange and solve that for height. So 1 plus the height squared is equal to 4. If I subtract 1 from both sides, I get that the height squared is equal to 3, and that means the height is the square root of 3. So we're just going to label that as the square root of 3. And so now we need to consider, what are those angles? Well, the angles in the equilateral triangle are all 60 degrees. So that means that angle is 60 degrees. And then the vertical line I drew down the top is splitting that in half, and so that becomes 30 degrees. And so if you use the conversion factor that 180 degrees is pi radians, what you end up getting is you end up getting 30 degrees is pi over 6, and you end up getting 60 degrees is pi over 3. And so those are two angles, and those are our other two special angles that we're interested in here. So we're going to do the same thing for sine, cos, and tan, but now of pi over 6 and pi over 3. So sine of pi over 6, well, that's taking this angle up here, and so that's going to be the opposite over hypotenuse. So the opposite side is 1, the hypotenuse is 2. So we're going to do 1 over 2. So that's 1 over 2. And when we take cosine of pi over 6, that's going to give me the adjacent side over the hypotenuse, so root 3 over 2. And when I take tan of pi over 6, that's going to give me the opposite side over the adjacent, which is 1 over root 3. And just like we did before, we need to rationalize the denominator by multiplying by the square root of 3 over the square root of 3. And so 1 times root 3 gives me root 3, and root 3 times itself gives me 3. And so that's all the special ratios for sine, cos, and tan of pi over 6. So now let's look at sine, cos, and tan of pi over 3. So we're focusing in now on that angle right there. And so sine of pi over 3 gives me the opposite, which is root 3, over the adjacent, which is 2. So root 3 over 2. Cosine of pi over 3 gives me adjacent over hypotenuse, so 1 over 2. You can see that the sine and cos of pi over 6 and pi over 3 are literally just swapped of each other. And then tan of pi over 3 is equal to the opposite side over the adjacent side, which is root 3 over 1, which is just root 3. So there we go. We've got special angles. What does that have to do with the unit circle? We're going to put those in the unit circle, but first, let's consider two things. Let's consider first what sine and cosine are in terms of the letters. So if I have some angle here, and I have turned my terminal arm from always starting here, the terminal arm always starts there on the positive x-axis, and I've turned it some angle in a counterclockwise direction. That's going to form some coordinate point out here that has x and y coordinates. And this is a unit circle, so what that means is that the radius is equal to 1. That's what you see. When you hear the word unit, think 1 unit. So the radius is equal to 1. And so what we can see is that if we were to make sine or cosine of this, where that gives me the x and y coordinates, then what I could do is the x value is along that side, the y value is along that side, and we form a 90-degree triangle there. And so what do those x and y coordinates have to do with sine, cos, and tan? Well, let's go ahead and make what sine is. So sine of an angle is equal to the opposite side over the hypotenuse. So it's y over r. Well, if r is 1, that means that sine theta is equal to y over 1, which is just y. Cos theta is equal to the adjacent over the hypotenuse. So that's x over r. Again, if r is 1, that means that cos theta is equal to x. And so what that tells you is it tells you that those x and y coordinates that are on the edge of that circle are equal to cos theta followed by sine of theta. And we have those values from what we found of the different angles. So in other words, if we know what theta is, then we know the direct value for x and the direct value for y. And that's a really powerful thing to be able to do because we can solve a whole bunch of problems using that. So now I'm going to go and I'm going to translate all of the pi over 4 things onto my unit circle. And so what we're going to do is we're going to start by drawing an angle of pi over 4 that's 45 degrees. And I'm going to write the angle over here just so it doesn't get too clogged in the angle spot, but that's actually the angle around from the x-axis. That's pi over 4. And then the coordinates that's going to give us, the x-coordinate followed by the y-coordinate, but the x-coordinate is cos of the angle. And so cos of pi over 4 is root 2 over 2. And the y-coordinate is the sine of the angle, and sine of pi over 4 is root 2 over 2. And so the coordinates on the unit circle at an angle of pi over 4 are root 2 over 2 and root 2 over 2. Now we're going to go ahead and do the same thing for pi over 6. And so that's a smaller angle. That's an angle of 30 degrees. And so again, that's the angle from the positive x-axis. And so that I'm going to label over here, just again, not to make it clogged. That's going to be cos of pi over 6. Well, that was root 3 over 2. And it's going to be sine of pi over 6. Well, that was 1 over 2. And so those are the coordinates on that end of the terminal arm of a unit circle for pi over 6. Let's now do it with the last one as well, which is pi over 3. And so pi over 3 is 60 degrees. And so that's the angle all the way around again from the positive x-axis to there. And so what that means is that pi over 6, it's going to have coordinates of the x is cos, so that's 1/2, and the y is sine, which is root 3 over 2. And so the easy way to remember this, if you were ever trying to reproduce this, is that when you have an angle that's less than 45 degrees, like pi over 6, the x-coordinate is going to be bigger. If you broke this down into a triangle, the x-coordinate is bigger than the y-coordinate. And so that root 3 is bigger than 1. And so that x-coordinate better be bigger. And then if you're looking at the other angle, pi over 6, you can see there that the y-coordinate is bigger than the x-coordinate. And so that y-coordinate, the root 3, is bigger than the 1 there. So that's a really easy way to keep that in mind. And then what you can see is, obviously for pi over 4, they x and y have the same coordinates. But the beautiful thing about this is it doesn't just apply to the first quadrant. So that's what I'm going to do in the next section. So let's extend this beyond the first quadrant. Remember, this is quadrant 1, this is quadrant 2, down here is quadrant 3, and over here in the bottom right is quadrant 4. And so we take the pi over 4 angle, and if we drew an angle of pi over 4 in the second quadrant, so that this angle here is pi over 4, remember we're always measuring our angles from the positive x-axis, so we measure it in a counterclockwise direction, so we go all the way around to there. Well, what is that angle? That angle is the equivalent of going all the way around here to pi, this is pi, and then going back pi over 4 to get up here. Well, this is an angle of 3 pi over 4. And just to fill in a few other things, if we're at 90 degrees, that's going to be pi over 2. If we're at 270 degrees, that's equivalent to 3 pi over 2. And then if we're all the way back, that's equivalent to 2 pi. So we could have those just as reference frames as we go around this. But 3 pi over 4, that is going to have very similar coordinates. You can see just because of symmetry. In fact, the x value is the only thing that's going to change. The x value is going to be negative now because we are on the negative side of the y-axis. And so the x value becomes negative. These are all negative x-axis, negative x values on this side here. But the y value stays the same. It's still above the x-axis, and so those are still positive y values. Same angle, because of that symmetry, the values are the same. We call those the magnitudes. They're the same, but that x-coordinate becomes negative. Now if we take that angle and we translate that into the next quadrant, I'm just going to subtract and get rid of a few angles that I've drawn there so that we can see this a little better. If we go into quadrant 3 and we draw again an angle of pi over 4 beyond pi in this case, well, that's going to be pi plus another pi over 4. That's 5 pi over 4. And so we need to get comfortable with our fractions for that. And so that would be an angle of 5 pi over 4. And that would have coordinates, again, that are very similar. But now the x coordinate is negative and the y coordinate is negative. And so we know the x and y coordinates of 5 pi over 4. Now if we take that and we draw that same angle in the next quadrant, this is the fourth quadrant where this angle here is pi over 4. Well, that's going to be a little bit less than 2 pi because 2 pi is all the way around. So we go 2 pi, we subtract pi over 4, and that gives me an angle of 7 pi over 4. And so that's going to have an x value that's positive because it's now on the positive side of the y-axis. So that would be root 2 over 2. But the y value is still negative because we're down below the x-axis. So negative root 2 over 2. And so there we have it. We've got all those special angles in all the quadrants from pi over 4. And so now let's do the same thing for pi over 6 and pi over 3. So if you take the pi over 6 angle and you put that in quadrant 2, one thing we always do is we always put that angle above the x-axis. It's always drawn from the x-axis so that the corresponding angle would be pi over 6, and you can see that obviously due to symmetry from the other side of the circle. And that means that we're going around from pi and we're subtracting pi over 6. Well, that's going to give you 5 pi over 6. So let's go ahead and let's label that as an angle of 5 pi over 6. That's all the way around from the x-axis to there. That's 5 pi over 6. And that is going to have coordinates that are the same magnitude as on quadrant 1. But the x coordinate is going to be negative for the same reason it was before. So we take the coordinate root 3 over 2 and 1 over 2, and then we put it into quadrant 2, recognizing that the x value becomes negative. We do the same thing now in the next quadrant. And so now we're going pi plus pi over 6. And so we end up getting 7 pi over 6. So that's an angle of 7 pi over 6. And that has coordinates of the x value is still negative, so negative root 3 over 2. And now the y value is negative, negative 1/2. Now we go into the fourth quadrant, doing the same thing yet again. Now we're going around 2 pi, but then we're subtracting pi over 6 from that. And so what we end up getting is we end up getting a value of 11 pi over 6, because 12 pi over 6 would be all the way around. And that has coordinates of positive root 3 over 2, because we're back on the positive x values, but the y value is still negative, so it's negative 1/2. And so we just take that and we change the sign based on what quadrant we're in, and we're able to figure out what the other values are, like shown. Now for the last one, pi over 3. So pi over 3, if we go into this second quadrant, we end up getting 2 pi over 3. We go 3 pi over 3, that's pi right there. Subtracting pi over 3, that gets us to 2 pi over 3. And so those values that we get there are, again, negative in this quadrant. So it's negative 1/2 and positive root 3 over 2. And then if we go down into quadrant 3, then what we end up getting is we end up getting an angle that is pi plus pi over 3. And so that gives me 4 pi over 3. And that's my angle from the x-axis. And that's going to give me values that are both negative now. So it's negative 1/2 and negative root 3 over 2. And then finally in quadrant number 4, we end up now with, we're 2 pi minus pi over 3. And so we end up getting 5 pi over 3. And so 5 pi over 3 gives me coordinates of positive 1/2, because x's are coordinates are positive again now, and negative root 3 over 2. And that is now the complete unit circle with all the special angles labeled on that. So anytime you have cosine of any of that, you can pull that out. And anytime you get a tan, then you can just say, well, tan, for example, of, let's say, 5 pi over 6, well, that's going to be equal to the opposite, which is y, over the adjacent, which is x. Well, the 5 pi over 6, this is the x, this is the y, and so that means that tan of 5 pi over 6 is going to be equal to 1 over 2 divided by negative root 3 over 2, because those are the same denominators, it ends up being 1 over negative root 3, which when we rationalize the denominator by multiplying the top and bottom by root 3 becomes negative root 3 over 3. And so that's the power of the unit circle, allowing us to solve all these different angles beyond the first quadrant, not only sine and cosine, those pull directly out of those coordinates, but also tan, and then also the reciprocal functions from that as well. You can see I've also added the 4 points where the circle passes through the x or y axes. If this video was helpful, please like and subscribe. Comment below if you have any further questions or anything I can make future videos on that you think would be helpful. And in the meantime, you can check out this video about more on trig identities and how we apply these.